All right, thank you. See if I can get this to work. All right. First, a brief history on this project. In 1996, Vito Bobrowskis published a paper in the Journal of Fire Protection Engineering, and he made a statement that you can see here. Main limitation of compartment fire models is that they generally are not capable of predicting fire growth, but only suitable for calculating the consequences of a user-specified fire. Now, we're 15 years later, and that statement probably largely still holds true, except that we have made significant progress in our ability to predict fire growth in a compartment, and that's primarily due to the increased use and availability of CFD codes like FDS. When you would use an approach like that, you would typically subdivide the large surfaces of walls, ceiling, floor, and possibly objects into smaller areas and smaller segments. You would assume that the thermal exposure for each of these segments is uniform, so that you have a uniform temperature across the segment, and you have a uniform burning rate. And there are different approaches then to determine how that segment will ignite and contribute and start pyrolyzing. Regardless of the approach that you're using, the problem is that you need to obtain some parameters, material properties, and typically that's a difficult task. There is actually a document already available that gives some guidance on how to obtain these parameters, a limited number of these parameters. It's an ASTM standard. This standard was published in 1994. It really has not changed very much since then, so it's obviously obsolete and needs to be updated, and this was recognized in 2008 by NIST, and they decided to award the grant to Worcester Polytechnic Institute, Southwest Research Institute, and the Society of Fire Protection Engineers. And the objective of the grant, the objectives of the grant are to update the content and expand the scope of this ASTM guide, and to develop a document that will serve as a basis for an SFPE guide. All right. In this SFPE guide document, we make a distinction between 4 different categories of models. The most complex ones are at the bottom. The least complex ones are at the top. The least complex one in category 1 are models where you would run some tests in a calorimeter, and you would just take that data and plug that into your compartment fire model. Category 2 is a little more sophisticated. There you would have an intermediate step where you take the bench scale calorimeter data and you would translate that into some material properties, things like the heat of gasification and the heat of combustion, and then use that in your compartment fire model to predict the pyrolysis. And model category 3 is a lot more sophisticated. That involves a more detailed calculation of the heat transfer through the solid, and if it's a char-forming solid, also through the char. However, in this case, it is assumed that the thermal decomposition occurs infinitely fast at a specified temperature, a pyrolysis temperature. And then model category 4 is even more complicated. Again, we have a detailed heat transfer calculation, but it's no longer assumed that the kinetics are infinitely fast, so pyrolysis happens over a finite region. Category 1 models, when you look at cases where people have used fire models, in the vast majority of these cases, you will see that the modeler typically would input the heat release rate of the fire. That's still how we normally do it. Now, where does that data come from? Typically, it's obtained in a furniture calorimeter. We call it a furniture calorimeter because it was developed originally to obtain heat release and mass loss rate data for furniture. But it can be used for all types of objects. Essentially, the object is placed under a hood that is connected to an exhaust duct. In the exhaust duct, we have instrumentation to measure the heat release rate based on oxygen consumption And then the object is also typically placed on a weighing platform so that we can measure mass loss rate. So that seems to be pretty straightforward, pretty simple. But there are some issues here, some things that need to be considered. In the next few slides, I'll be talking about a few results that we obtained in an ongoing project for the National Institute of Justice. And I just wanted to make you aware of the fact that what I'm going to be saying is my opinion and not that of the Department of Justice. So, this shows a test in progress on a furniture calorimeter on a one-seat sofa mock-up. We have to show at least one flame, I assume, doing a conference like this. What are the issues here? You can run this test and you obtain some data, and maybe somebody else obtained the data for you and you find it in a handbook or something. You have to be very careful when you use generic data. And to illustrate this, I show an example here of a one-seat sofa mock-up that we tested. You can't really tell these two mock-ups apart. They're both built with polyurethane foam padding and a cotton fabric. And they were both ignited the same way with a California TB133 burner. And then you look at the bottom and you can see what's left after the test, and you can't really see much difference between the two. But when you look at the heat release measurements for those two sofa mock-ups, you can see quite a bit of difference. The blue curve is for the sofa with low-density polyurethane foam, and the red one is for a sofa with a high-density polyurethane foam. So polyurethane foam generically can mean different things. So you have to be very careful when you use data either from a test report or from the literature. There are some differences. Another issue is measurements are not without error, so you have to account typically for measurement uncertainty. There is actually an ASTM standard, the ASTM E2536, that outlines the process and how you can estimate the uncertainty of measurements, heat release measurements in particular. This shows an example. This is the one-seat sofa, one of the two, the high density, I believe. And then you can also see the uncertainty bounds there, expanded uncertainty bounds. They're about plus or minus 10%. So you can calculate that for these experiments, and you can basically account for that in your analysis and propagate the uncertainty through your analysis. More importantly even is the way the item was ignited. There is some uncertainty regarding that. The type of the ignition source is an important parameter, and where the sofa was ignited is another important parameter. This shows an example here of two used one-seat sofas that we tested. In one case, we tested the sofa with 2 ounces of gasoline distributed across the seat cushion. And in the second case, the red curve, we used a small ignition flame, gas flame. The two curves are largely identical. The only difference between the two, the primary difference, is that the red curve is shifted over about 3 minutes. And you would be able to account for that relatively easily in your modeling exercise. Now we have done a series of tests where we assessed the effect of using different ignition sources, and it wasn't always like this. So sometimes you have to be careful with that. Another surprising result that we obtained is where do you ignite the sofa? On the next slide you can see a 3-seat sofa mock-up. The heat release rate was measured in 2 ways. In the first test, we applied the burner to the seat cushion on the right, and that's the blue curve. And in the green curve is when the burner is applied to the center seat cushion. And what happens is that when you apply it to the seat cushion on the right, that's where the fire starts, and the fire will just migrate to the other side. While it's burning out on one side, it will just involve new material on the other side. And that's why you see this relatively steady burning behavior. While when you ignite it in the center, the flame spread to the 2 armrests, and then where the armrests get involved, you have this peak. So how or where the item is ignited is an important parameter as well. And often when you find data in the literature, it's not even mentioned how the item was ignited, so it can be important. Two other effects that perhaps need to be considered, or issues, enclosure effects. We get data from testing in an open calorimeter. We then use that to model how fires behave inside an enclosure, and that enclosure can have an effect on the burning rate. It's very difficult to account for that, but that's something that may have to be incorporated or considered. And the last bullet here is Kevin mentioned this morning the fire PRA analysis for nuclear power plants. One of the primary uses of fire models is to determine when certain targets like cables, when they exceed an ignition threshold or a failure threshold, and that is linked to a particular heat flux or a particular temperature. And it's important in calculating that temperature or heat flux, it's important to know what fraction of the heat that is released by the fire is in the form of radiation. We typically don't measure that, so where do these numbers come from? And that's another thing that is addressed in the guide. All right, so the approach that we can use for objects, unfortunately, we cannot use for materials that are spread out over large surfaces like linings. In that particular case, what you see here is, as an example, a room corner test setup where we're interested in calculating how the fire spreads over the surface of the walls. And in order to do that, you would have to subdivide the walls into these smaller segments and basically use the approach that I mentioned early on. When you use a Category 1 model to do that, you could basically obtain some ignition times and heat release data in a device like the cone calorimeter or the fire propagation apparatus. You obviously have to obtain that information at least one heat flux as a minimum. You could choose a heat flux that is somewhat representative of the scenario that you're trying to model. Again, Vito Bobrowski has written a paper with some guidance on that is very useful in that respect. But it's even better if you could run tests at multiple heat fluxes, and then you can better account for the effect of time-varying exposure conditions on the burning rate, the pyrolysis rate. When you do that and you have data at multiple heat fluxes, you need to have a mechanism to determine how the ignition time is affected of each of these segments when you have a time-varying heat flux, and also once the segment ignites, you need to have a mechanism to determine how the heat release rate is affected. One important comment that I would like to make here is that we test these materials in a device like the cone calorimeter under specific conditions. The test specimen has a certain thickness. It's backed by a standard substrate. Typically, it's ceramic fiber blanket. Now, in reality, the thickness of the material as it is used in the room might be different. It might be backed by a different material, and accounting for those differences is very difficult, but may have to be considered. Here are some typical curves. In the two chapters that deal with Category 1 and Category 2 models, the examples that are given there are for two materials, a typical charring material, Douglas fir plywood, and then a typical thermoplastic non-charring material, PMMA. These are the curves that you would get when you test the Douglas fir plywood in a cone calorimeter at different heat fluxes, 25, 50, and 75 kilowatts per meter square. This is what you would get for something like PMMA. And you can immediately see in the previous slide that the behavior is very different in terms of Douglas fir plywood. You have an initial peak, then the burning rate goes down, and then toward the end, because the material is backed with insulation, the burning rate goes back up. For PMMA, it's relatively constant throughout the entire test, and it's only toward the end, again, because the material is backed by insulation, that you see an increase in the burning rate. But this is relatively close to steady burning, while the plywood obviously is not. All right, first question, if you want to recreate, or if you want to use that information from tests at different heat fluxes to determine what the ignition time is in the actual room scenario, you would need to interpret the data in terms of material properties like thermal inertia and ignition temperature. When you scan the literature, you'll find about a dozen methods to do that. In the guide, we're really only focusing on two different methods. One of the two methods is illustrated here, method developed by Quintier and Harkerode, and it basically consists of determining the critical heat flux for ignition, that is the heat flux below which ignition no longer occurs, and that's done by running repeated tests at lower heat fluxes until ignition no longer occurs. And typically a period of 20 minutes is assumed to be the cutoff. And you can then plot the ignition times that are obtained at different heat fluxes in a graph like this. And from the slope of the line through these data points, you can obtain a thermal inertia. And from the critical heat flux, you can determine what the ignition temperature is. So those are the properties that then you can use in a compartment fire model to determine when a segment would ignite when it's exposed to a time-varying heat flux. Now you can see one data point here that was eliminated from the analysis. This method, the underlying theory basically is valid for relatively short exposure times, and when the exposure times become too long, then the data points no longer follow the trend, and you have to eliminate data points like that from the analysis. We're using a methodology that was proposed by Spearpoint and one of his students in a recently published paper to scrutinize the data that are obtained in, from ignition experiments like this. All right, well, I think I'm going to have to rush through there. This is the other method. The next question is the heat release rate. Once you know when the material ignites, you need to know what the heat release rate is as a function of the heat flux. And in order to do that, you have to transform the time axis and basically express the heat release rate as a function of a progress variable. In this case, total heat release is used, and you can just interpolate depending on the heat flux that you have at a particular time, based on the total heat release at that time. Category 2 models rely on these properties that we determine on the basis of the bench scale measurements. The primary property that we consider here is the heat of gasification. Heat of gasification is the amount of energy that is needed to gasify a mass unit of the material. And you can essentially, if the material burns at a constant rate, then you can run tests at different heat fluxes and plot the mass loss rate as a function of heat flux, and determine from a plot like that and a linear fit through the data points, you can determine what the heat of gasification is. And then you can use that, in your compartment fire model to determine what the mass loss rate of the segment is depending on the incident heat flux, which the compartment fire model will calculate for you. This shows some examples for plywood. You can also use heat release rate. In this case, the heat of gasification would be determined from the slope, heat of combustion divided by the slope. One problem with this approach is that it assumes steady burning, while some materials like plywood do not burn in a steady fashion. And you're essentially assuming that the material burns like you see here. You can assume that it burns at a peak heat release rate, and then the idealized representation of this heat release curve is this. You can assume that it burns at the average rate, and then your idealized version of the heat release curve is the one that you see here at the bottom. In both cases, you'll make some errors in terms of estimating what the mass loss rate of the heat release rate is. Okay, for Material like PMMA works a lot better because the burning rate is fairly steady, so average seems to work fine. Category 3 and 4 models, those involve these complex heat transfer calculations, and the difference between the two, as I explained, is in the assumptions of infinitely fast versus finite pyrolysis kinetics. The properties that need to be determined are listed here. Thermophysical properties, K, rho, and C, both for 3 and 4, surface emissivity, absorptivity, pyrolysis temperature, that's only for category 3 models, heat of pyrolysis for 3 and 4 again, and kinetic constants only for 4. The general strategy that we have in the guide is to measure as many parameters as possible and then estimate the remaining parameters from optimization. And that process is described for a number of example materials, PMMA, cardboard, and fiber reinforced plastic. So this is the outline of the guide. Most of it is in chapters 2 to 5, which explains for these 4 different categories of models how you go about. As you see on the next slide, description of the model, how the parameters are defined, how the parameters can be obtained, either through direct or indirect measurements or measurements in combination with calculations, and then some examples for PMMA and plywood in chapters 2 and 3, and then the other 3 materials, PMMA, cardboard, and FRP in 4 and 5. I'd like to thank Kevin McGrattan for this grant support, and I kind of skipped the last line here. I had expected to have a draft ready at this conference, however, it's going to take a little more time. I don't have a paper in the conference proceedings, but my intent was to make the draft available for those people who are interested in reviewing it, and it should be available in a few weeks from now. That's it.